Hi, I'm Matthew Hoffman, working alongside Andrew Butt and Chiyu Arthur Chung, and I'm going to be talking about how we're modernizing HLS using modular compiler infrastructure, as well as evaluating the gap that still remains with commercial tools. So we know Xilinx Vitis is a streamlined tool flow for getting high-level code onto hardware accelerators quickly. But Vitis's business-driven priorities means that the tools make a lot of trade-offs. So Vitis only supports Xilinx-made FPGAs, and the tool flow is not very modular. Academics are, constantly hacking the vendor tools to suit their needs. Even bigger picture, I think the C front end is a good example of the phrase, premature optimization is the root of all evil. And what I mean by that is having a purely C++ front end makes leveraging the FPGA hardware difficult because it requires so much code reformulation and carefully considered pragmas. So we want to suggest that HLS code that requires users to specify things like the memory microarchitecture as not being very high level. And we do see this end result that HLS C code really can't be moved to new contexts, and HLS C code has really bad portability and maintainability. So then what can open source HLS do for us then? Well, the state of open source HLS is, scattered across many projects, and many efforts are works in progress. However, we think CIRCT is different because it brings a truly modern optimizing compiler methodology to accelerator compilation. So, when we're talking about old HLS, which is what we're calling Vitis and some other open source HLS projects, they use conventional compilers like LLVM to do their front end transformations. And this results in, hacky and tightly coupled solutions that are, really starting to hit a wall in terms of extensibility and ability to handle new emerging applications. On the other hand, with CIRCT, transformations and optimization passes are understandable at every level of the IR, and they're completely separated and interoperable with each other. So really we want to say that monolithic C-to-Verilog synthesis is just not a very sustainable infrastructure. And I think good evidence for this is the creation of code generators that output HLSC. So on one hand, they're doing this because HLSC code is not very manageable to write, but also because there doesn't really exist HLS compilers that can take intermediate representation as an input. So this is what CIRCT can do though. So it uses intermediate representation to interchange between its code transformations. However, CIRCT is very incomplete, and that's where we come in. So CIRCT is missing a scheduling algorithm, the control programs for these schedules, and then finally, loop pipelining with memory resource constraints, and much more that we don't get to handle yet. So our contribution starts with list scheduling. We implement list scheduling very similar to Lecture 10 based on static priorities based on ALAP times. And then from a schedule, we construct a control program. So once a schedule exists, we lower it to a control program embedded in our own dialect called STG, which stands for State Transition Graph. Once we have this control program, we can then write it into a new representation called Calyx IR. And Calyx has its own compiler that can produce the Verilog that can finally be put on an FPGA. And then finally, very important for performance is resource-constrained loop pipelining. So in order to have results that are competitive with Vitis, we need to have loop pipelining with memory resource constraints. So this means implementing modular scheduling and then having something to construct pipelines that can be compiled. So these three things definitely have direct analogs within Vitis, but we want to show how the methodology is different. So first is different is, Vitis is opaque because it's closed source. So for all intents and purposes, it's a black box to us. And two, modeling the problem is just writing C code. This contrasts with our method where we start with a higher level primitive that describes our application, like matrix vector multiplication, and we gradually lower it with transformations. So this slide sort of explains the middle end of our compiler. And then when we're talking about Calyx, that is our back end of our compiler. So once we have a control program, Calyx is able to produce a Verilog for us. So the benefits to our approach is really that when the user is leveraging higher level primitives, either directly or via a domain specific language, the optimization passes have better context to do their job. So in the end, you get, better results for differing target hardware architectures, and you have many more opportunities for higher levels of automation. So since our scheduling and pipelining implementations are modeled as fully separated, interoperable compiler passes, we have much better debugging and extensibility, and the better separation of front-end transformations from scheduling allows us to take advantage of a wider range of optimizations at different levels. So here we have some designs compiled through Vitis in our flow. We're looking at linear algebra operations, and the best result we get here is when we're doing vector add pipelining. So we get the same execution time. However, for things that are more sequentialized, we're getting worse runtime. And it's really showing that, the FSM generation for Calyx has some inefficiencies that need to be worked out. Because we also see this on the hardware side of things where we're using a lot more flip-flops and a lot more LUTs to do the same thing. So, CIRCT is kind of losing in the sequential programs, but what if we force Calyx to produce massively parallel kernels? So we would hope that, FSM generation would matter less here. And here we can see that, yes, the FSM overhead is small, but a component of it we think is still scaling with the computation. So here we have a vector add application where we're just increasing the vector length. So as we increase the vector length in the CIRCT case, since it's not instantiating an FSM efficiently, part of the FSM has handshaking signals, and all these handshake signals are growing with the added adder hardware. So this is something that needs to be fixed within Calyx. So, with our improvements to CIRCT, we see that it's still much better than what we were working with at the baseline level. We get improved runtime of pipeline programs, and even if we don't have the best performance, at least we can compile it all. So with our new features, we have a much greater range of designs that can be compiled end to end. And with pipelining, we are seeing that they are speeding up unpipelined programs, even if they are still lower than Vitis. So, our most competitive designs are pipelined, but the limitation there is the types of pipelines we can produce is very limited by the lack of support for more complex memories. So this is important for literally everything. The pipelining case, the unpipelined case. So the future work here is to really implement multi-ported memories and array partitioning in CIRCT. So, besides that, the majority of our designs are worse than Vitis, from one, Calyx inefficiencies, and two, a lack of operator chaining, both of which will be addressed in the future. And if you want to see what's going on with CIRCT, you can check it out at its GitHub. And I'm going to hand this off to Andrew Butt to quickly do a demo.
Thanks, Matt. So here I have the Calyx code that we've generated for a vectorized add. And this is specifically the pipelined example. So you don't have to go into the specifics of how Calyx works, but you can see here we have our control program, and this is encoding how the pipeline runs to do a 8x8 vectorized add. I have this pre-compiled into a Vitis XCL bin, which allows us to actually run this on a real data center FPGA. And I have some host code set up to be able to run it. And so you can go ahead and run it, and we see that the results produced by our HLS on real FPGA match those of the CPU result. Thank you.